So in the second question, again, a table is given to you, and this is the results of an odometer test on a specimen of saturated clay. However, in this question, the graph corresponding to this table is not given to you, and you have to be able to draw it on a logarithmic scale. So if we draw the graph corresponding to the results of this test, it would be something like this graph that is shown here. In the second part of the question, it says that a layer of the same clay that were tested in the lab, which has an 8-meter thick, lies below a 4-meter depth of sand, and a fill of unit weight of 21 kilonewton by cubic meter is placed on these two layers. So we have a layer of sand, depth of 4 meter, and then we have a layer of clay with a depth of 8 meters, and then we have a load on top of these two layers. So the load corresponding to the fill is basically just the unit weight of the fill times the depth of it. So it's 84 kilonewton per square meter. And the question asked the final settlement due to consolidation of the clay. And in the second part, it says if we remove this load again, how much heave would take place due to swelling of the clay. So in the first part, again, we have a layer of sand, and we have a layer of clay. This is 4 meters, this is 8 meters. This is the initial situation, and then we have the same, but with an external load on top of these two layers. And the consolidation of the clay layer is asked from us. So in order to determine the settlement in the clay layer, we can consider the whole clay layer as one layer, or we can divide it into sub-layers and calculate the settlement of the sub-layers and add them all together to get the total settlement. It's like finite element method. The more sub-layer that you have, the more precise results that you would get. But on the other hand, it will make your calculation process more difficult. So you have to be careful and kind of optimize the number of sub-layers that you're choosing. So in this question, we're gonna divide this 8-meter clay layer into 4 sub-layers and each of these sublayers has a 2 meter depth. So this is our clay. We're going to divide it into 4 sublayers, and then we have to determine the value of settlement for each layer. So this is 8 meters overall. We have a sand layer on top of it, the depth of 4 meters. And now we have to determine the value of settlement of each layer. So for this purpose, we have to consider the middle part of each layer. So this is the first one, this is the second one, this is the third one, and this is the fourth one. And the equation that we are going to use is SE equal to E0 minus E1 divided by 1 plus E0 times H. And H is the thickness of each layer, which is 2 meters or 2000 millimeters. So for each layer, if we determine the value of E0 and E1, so E0 being, I'm going to change this to 0 and change this one to 1. So E0 is corresponding to the initial situation, and E1 is corresponding to the final situation. So if we determine E0 and E1, we can put it in this equation and determine the value of settlement for each sublayer. And in order to determine the values of E, we can use this graph, and by having the values of effective stresses, we can determine the values of E corresponding to these points. So I'm gonna draw a table and show you what I'm gonna do. So this is layer 1, 2, 3, 4. They have sigma prime 0, we have sigma prime 1, we have E0, we have E1, we have E0 minus E1, and then we have SC. So this column is corresponding to this condition, and this column is corresponding to this one, and same as E0 and E1. So E0 is read from the graph based on this value, and E1 is read from the graph based on this value. So at each of these points, we have to determine the value of effective stress before and after applying the load. In the first layer, it's at a depth of 5 meters, and there's no load before putting the fill, so we only have 5 meters of a soil, of 2 soils actually. since they have the same saturated unit weight, we can use the same value for them. So we have 5 times 19, which is the saturated unit weight of the soils, and we have to deduct this unit weight of water. So this value is equal to 46. This is before applying the load, and after applying the load, we can add this value plus the load, which is 130. For the next layer, we are at a depth of 7 meters, and the value is equal to 64.4, and this is 64.4 plus 84, which is equal to 148.4. And the next 2 layers, we use the same method. This is 9 meters, this is 11 meters. I'm just gonna write the values. This is 82.8, and this is 166.8, this is 101.2, this is 185.2. And now that we have these values, we have to read the values of void ratios corresponding to these effective stresses using the graph that we have. So I'm gonna just do some examples. Let me use another color. So for this one, the value of effective stress is 46. So say this is 20, 30, 40, and this is 46. The value of E corresponding to 46 is very close to 123 or 124. So we put 1, 2, 3, 6, and for this one, 130. This is 100. This is 200. This is around 130. I'm just gonna go here, and the value of E corresponding to this point would be 1.123. And for the other values, we use the same concept. I'm just going to write the values. So this is 200, 1.108, 1.172, 1.095, 1.150, 1.083. The value of E0 minus E1, 0.113, 92, 0.077, and 0.067. And for SC, they're going to use this equation. So we have this, and we have this, we can determine this. I'm just going to write the final values. So this is 101, this is 84, this is 71, and this is 60. So we have 4 layers. We calculated the settlement values for each layer, and now we have to add these values together to calculate the total settlement of this 8-meter layer, which is equal to 318 millimeters. And this is the final settlement.